for the challenge. Now, it's not all super challenging, but some of it is, some of it's medium challenging. So the first part is medium challenging. So let's read it. So it says a 10 kilogram box of holiday lights is gently accelerated from rest at x equals 0 meters with a force of 2x, well, that force. Over the first 4 meters across the icy driveway, find the power at 0 and 2 meters. Okay, now the problem here is when I talk about power, I think, okay, instantaneous power. Instantaneous power is d work dt. Well, in order to do this, I need a work function that's in terms of time. And all I can do is, I can't find a work function in terms of time if I have a force function in terms of position. So I'm going to have to go the other route. I'm going to have to multiply the force dot the velocity. Well, I do have a force function at these individual positions, so that's doable. So now I just need to know the velocity at those positions. And so in order to do that, in order to find that velocity, I'm going to use the work kinetic energy theorem here to go ahead and use the force to find the work and then find that kinetic energy. So there is work in, there is no work done by friction. It does have kinetic energy at the end. It doesn't at the start. It's on a level surface, so there's no UGs and there's no spring. So this is just our work kinetic energy theorem. Since our force is a variable, we'll need to integrate. So I'm going to integrate from, well, I guess we should probably make this easier. If I integrate from 0 to 0, how much kinetic energy is there going to be? 0. So that means there's 0 velocity. And so at x equals 0, or meters, the power is going to equal 0 watts because V is equal to 0 meters per second. Okay. For the other one though, for the 2 meter one, we do have to do this. So we're going to go from 0 to 2 of our negative 2x squared plus 7x plus 4 dx is going to equal our 1/2 mv squared, where our m was 10 kilograms. Go ahead, we should plug this in. We get a v of 16.6 meters per second when we solve that. We can then plug that in over here, so our power is going to be our force, so negative 2 times 2 squared plus 7 times 2 plus 4. And I'll note that this is all in the x direction. This is a pushed horizontally, and so it is in the same direction as the velocity. So both of these are my I hat components, in other words, is what I'm saying, times the 16.6 meters per second. I believe that's got a line over the top of it. And when I plug this in, the power I get is 166.7 watts of power. All right, fair enough. So now I found the power at x equals 0 and x equals 2. Now it wants me to find the location when the power is a maximum. So I want to maximize this function for power. Okay. So if I think about this, all right, in order to do this, what we're going to need to do is we are going to need to create a function for velocity. So I can do that here by taking my integral and talking about what is my force at 0, okay, or my power at 0, I guess. So I have, what, negative 2x cubed divided by 3 plus 7x squared divided by 2 plus 4. That's all multiplied by 2 divided by 10, the mass, and square rooted. That is my velocity. And so to find the power, I need to create an equation. So my power is going to be right there. So the force is negative 2x squared plus 7x plus 4, all times the square root of 2/10 times negative 2x cubed divided by 3 plus 7x squared divided by 2 plus 4. And if I want to maximize a function, all I have to do is find dp dt, or dx I guess in this case, and set it equal to 0. Find the x values and plug them back in and get the maximum power. I don't know about you, but that looks like a heck of a derivative to take and then set equal to 0. So you're more than welcome to give it a shot.